Hello everyone, I'm Akshat Ramachandran, a second-year PhD student at Georgia Tech advised by Professor Tushar Krishna. We are happy to present our latest ECCV work, CLAMP-ViT, Contrastive Data-Free Learning for Adaptive Post-Training Quantization of ViTs. This work was done in collaboration with Intel. Model quantization has emerged as a popular technique to achieve memory and compute-efficient deployment. Quantization reduces the memory footprint and improves computation speed of a model by mapping full precision weights to reduced precision formats. There are two main categories of quantization: post-training quantization and quantization-aware training. In this work, we focus on post-training quantization. Post-training quantization, however, requires access to a calibration data that is often drawn from the training data set. This may be infeasible in situations involving privacy and security concerns, making these techniques ill-suited to yield optimal performance. Data-free post-training quantization, on the other hand, generates the synthetic data that is required for calibration from Gaussian noise using information embedded in the layer weights. However, existing data-free quantization techniques have significant challenges that limits their widespread adoption. Firstly, the generated synthetic data is overly simplistic with uniform backgrounds, resulting in a lack of realism that affects the model accuracy when used for calibration. Secondly, the metric recent techniques like PSAC-ViT V1 and V2 employ to guide data generation ignores the spatial sensitivity, reducing synthetic data robustness and its informativeness to the quantization process. This creates a jagged loss curve that results in a non-optimal quantization solution when the optimization gets trapped within local minima. To mitigate the disadvantages in existing solutions, we propose CLAMP-ViT, a novel technique that leverages the architectural characteristics of transformers of patch processing to generate spatially sensitive data, along with a novel contrastive learning metric that induces spatial sensitivity and exploration of semantically meaningful relationship among patches using our contrastive learning metric. And finally, to ensure the generated data is informative to the quantization process, we employ cyclic adaptation between data generation and quantization. The CLAMP-ViT algorithm is divided into two distinct stages. Stage 1, synthetic data generation, and Stage 2, quantization. We follow a cyclically adaptive strategy between these two stages to ensure that the generated data is always optimal and as informative as possible to the quantization process. The goal in Stage 1 of synthetic data generation is to generate semantically rich and meaningful images that can exploit interpatch relations. For each anchor patch of an MHSA output or multi-head self-attention output in the quantization model, we first locate positive and negative patches from the same layer ID in the full precision model from a neighborhood of the anchor spatial position. We then leverage our proposed contrastive learning objective, which is highlighted here, that operates to maximize the similarity between the anchor and positive patches while minimizing similarity with the negative patches. We then compute this contrastive learning loss for all layers across the entire model to get the contrastive learning objective. We then compute the sample generation loss by combining this contrastive loss with the output loss, which is measured using mean absolute error, and minimize that to generate the synthetic data that is required for quantization. Once in Stage 1, the synthetic data is generated, in Stage 2, we employ a layer-wise evolutionary search with a local contrastive loss-based fitness function to rank suitable quantization parameters from a large search space. The evolutionary search process is divided into 4 stages. In Stage 1, we employ candidate initialization, where we randomly initialize layer-wise quantization parameters as a vector equal to the length of the number of layers in the model, where each element corresponds to the quantization parameters of each layer. For example, for integer quantization, the quantization parameters can be the bit width and the scale factor. Once these quantization candidates are established, we rank these quantization candidates based on our fitness function. And then we perform regeneration and crossover following standard evolutionary search practices to from the best performing quantization candidates to progress the generation of more and better quantization parameters through our search process. We then employ diversity promoting selection to add some noise and make the search process a bit more robust, and then finally, we perform all these 4 stages for C cycles for each layer and for P passes through the whole model until convergence is reached. And once the convergence is reached, the top performing candidate has the best layer-wise quantization parameters for our quantized model. Let us now observe some qualitative results of the generated data samples for the image classification task compared with recent state-of-the-art quantization techniques PSAC-ViT V1 and V2. Evidently, the data generated by CLAMP-ViT is semantically meaningful, with the subjects placed within meaningful and consistent background as compared to the simplistic and noisy background of previous works. Similarly, we also demonstrate qualitatively the semantic segmentation performance of our method and observe that at extreme W4A8 quantization, the generated segmentation mask is largely similar to that generated by the full precision model. And it's important to note that all this is data-free. Quantitatively, for fixed precision quantization performance on ImageNet, we achieve approximately 2.2% improvement over other data-free quantization techniques and approximately 1% improvement over other post-training quantization data-dependent techniques, which sometimes require 1,000 calibration images from the training data. Particularly, for extreme W4A8 quantization, 4-bit weight and 8-bit activation, our method shows significant performance boost over all the existing alternatives despite being data-free. This, we believe, is because of the method ensuring informativeness of the generated data to the quantization process. Importantly, CLAMP-ViT is the first data-free quantization technique to achieve mixed precision quantization on a variety of vision tasks. Here we show results for 2 tasks: image classification and semantic segmentation. Clearly, CLAMP-ViT achieves comparable and even better performance compared to other data-dependent mixed precision quantization techniques and achieves a higher compression factor compared to these techniques. In the figure here, we show the runtime and top-1 accuracy of different techniques on an NVIDIA Titan GPU for DEITS model. CLAMP-ViT achieves significantly higher accuracy compared to the other methods, with only a minimal increase in runtime of approximately 5% compared to the best data-free quantization technique. On the bottom right, we also report the reduction in model size and bit operations per second of mixed precision quantized DEITS compared with PSAC-ViT V2. CLAMP-ViT achieves approximately 10% lower model size in MBs and bit operations per second when compared to PSAC-ViT V2, while yielding more than 3% improved accuracy. This concludes the presentation of our work CLAMP-ViT. For more information on our work, please scan the QR code here on the right, and if you would like to contact the authors of this paper, please scan the QR code here on the left. Thank you so much for listening.